This lesson deals with Supplemental Problem 12.6. You can find this problem in the ECE202 ebook in Chapter 12, starting on page 21. Symbolic Splice is a software package that is an analog circuit analyzer and approximator. Symbolic Splice performs the .ac analysis in Splice symbolically, but also has an optional numerical evaluation, and you can also set a user threshold to do approximations. The output of S-Splice is sorted by like symbols and by powers of Laplace operator S, or by a user-specified symbol. S-Splice can also identify second-order transfer functions and can symbolically solve for the values of H for a low-pass, high-pass, bandpass, or bandstop filter, as well as omega naught and Q naught. I'd like you to download the student version, which is a demo version, of Symbolic Splice, which is fully functional, but limited to a 6x6 matrix. You can find this on my website by following the Symbolic Splice link. Download the file and unzip it. It does have a password protection, and it's lowercase symbolic. Redo Supplemental Problem 12.5, but using Symbolic Splice. Instructions for running Symbolic Splice can be found in the file Frequently Asked Questions, and this is 5 lines below where the zip file was located. Symbolic Splice has a model for an ideal op-amp with the following definition. Let's begin with the letters XOA, and then you can have a name. This could be a number, a part number, or anything you wish to pick. The first node is the plus node, the second is the minus node, and the third node is the output node. From Supplemental Problem 12.5, we had this active filter, and we numbered the nodes 1, 2, 3, and 4. That's also valid for Symbolic Splice. Now we wrote a pSplice file on page 19, and I'm going to rename that as active_filter.cir, and I can drop off some things that are particular to pSplice. So just like Splice or pSplice, we have to have a title and a .in for Symbolic Splice, and then just a description of the schematic is all that's needed. We had an input voltage between nodes 3 and 0. It was a phasor with a magnitude of 1, but the default value is always 1 in Symbolic Splice. It's because every node becomes a transfer function. Then we have the resistors R1, R2, and R3 between 3 and 1, 1 and 0, and 2 and 4 with values, and C1 and C2 between 1 and 2 and 1 and 4, again with values. Our op-amp was between plus, minus, and output. The plus terminal was node 0, the minus terminal was node 2, and the output was node 4. So by double-clicking on the EXE file, a menu comes up, and I gave it the file name again, active_filter.cir. So let's see what happens when you run the program. The first line is the input file, and I just typed the file name, active_filter, and the extension is assumed to be .cir. And this file is in the same directory as the EXE file of Symbolic Splice. If it isn't, you have to give a path. If you hit enter, it comes back with an output file name based on your input file name and the extension .det. I'm going to leave that alone, so I'm just going to hit enter. Then we need to ask you a series of questions about what you want analyzed symbolically or numerically. So the first question is, determine string sorted according to orders of some variable. I'll say no here because we're just going to sort by the Laplace operator S, which is the default. Numerical evaluation of the results? Yeah, let's do that. Let's evaluate the formulas. Next, discard terms if their magnitude falls below a threshold. I'll say no here. This is the part of the approximation of Symbolic Splice. We're going to solve for exact values. Check and solve for second-order filter functions. Yeah, let's see if this is actually a bandpass filter or not. When you say yes, it's going to come back with a file name, have the same base name, but then the extension will be .fun for filter function. I'm going to hit enter, so it's going to put that as my default result. Last question is solve for a variable or expression, and I'll say yes. You don't have to have an expression. Sometimes just having the matrix is very interesting or very useful in calculating things. Here I want to take a look at what is my voltage gain in my circuit. The program comes back with the variables that are available, and in our circuit we also had a node voltage 2, but that was sitting at 0 volts to grounds. Symbolically it would just be equal to 0, so we're not going to let that be a possible output string. It also tells you about ignoring nodes 5 and higher. They are used for internal numbering. In a particular example we're doing, it wasn't necessary to do that, but in some other circuits you'll find that there are node numbers that are higher than your highest node number, and we use that as an internal numbering scheme. You can also have mathematical operators on your voltages. We won't use that right now. Let's take a look at node voltage 4. So let's say V4. You could also say V parentheses 4 would also accept that too. Do you want to solve for another variable expression? No, we'll just take a look at the output. What's shown below is the output of the file active_filter.det, and I open this in a word processor. So here's our title, first line of our input file, and here's the matrix that was used to solve for the voltages in our circuit. We asked for node voltage 4, so first gives me the numerator sorted by powers of S, and so here are all the things that had one power of S in it. It's a minus SC1 times G1. Numerically it's equal to this. Then next is the denominator of V4, and it's also sorted by powers of S. So there was an SC2 times an SC1, Things that just had one power of S was SC2 times G3 plus SC1 times G3. And things that had no S's in it were G3, G2 plus G3, G1. Let's put that together now as an expression. So V out over Vn is going to be equal to V4 divided by 1 volt. And that's going to be our numerator, which is SC1, G1. And then I've got, for my denominator, I've got an S squared, C2, C1. And then I have S G3 times C2 plus C1. And then lastly, I have G3 common, and I have a G2 plus G1 times that. And this is the same equation we had on page 18. So symbolic splice works with conductances and admittances and creates strings of combinations. Numerically, this last expression is also evaluated, and we can put that together in the following. So grabbing my numerator terms, from on top I have this value times S, and then this term times S squared, this term times S to the 1, and then this term times S to the 0. Then I divided numerator and denominator by 4 times 10 to the minus 14th, and that gave me in the numerator a minus 384.615 times S divided by S squared, and then dividing this through I get 100 times S, and then dividing this through here I get 38.4615K. And that's exactly the same expression we had on page 19 with a little bit more accuracy to it. We also asked the program to identify filter functions, and so our active_filter.fun file is shown below. And again, I open this in a word processor. It gives me my title of my input file in the first line, and then it tells me what second order parameters it was able to identify. Now in the denominator of our transfer function, we have an omega naught and a q naught, and actually found that symbolically. And then also evaluate it with our numerical values of our r's and c's. This is the square root of C2 times C1 times G2 plus G1 divided by C2 plus C1 square root of G3. And that was 1.96116. And that's the same value we had calculated on page 19. Omega naught squared is G3 times G2 plus G1 divided by C2 times C1. It then takes the square root of that and divides by 2 pi, and I get 31.2129 hertz. And that's exactly the value we had on page 19. Symbolic splice then takes a look at the numerators and determines the filter function. In this case, it identified node voltage 4 as a bandpass filter, and then found the value of H naught, which we'll call H sub bandpass. And it was equal to minus C1 G1 divided by G3 times C2 plus C1. And its numerical value is a minus 3.84616, same value we had on page 19. Now these forms of Q naught, omega naught squared, and H are not like how we usually write our equations. This is a line output format in our software. Let's rewrite this in a format more like what we do in the class notes. Taking those expressions for Q naught, omega naught, and H sub bandpass as listed above. It's got that here, here, and here. And then let's clean this up a little bit. Let's replace G3 by 1 over R3. G2 plus G1 is the parallel combination of R2 and R1 reciprocal. And then for omega naught, do the same thing. This is going to be R3, and this is going to be R2 in parallel with R1 reciprocal, right over here. And then this becomes R1, and this becomes R3. So not only do we have the numerical results, like we would get out of a numerical program like SPICE or PSPICE, but we also have the symbolic results. So we can see what's controlling these three parameters. And of course, we can use this to do a design procedure and be able to then pick the values of the R's and C's in our filter. There are a lot more options in the Symbolic Splice program, and you can follow links on my homepage with a series of application notes showing how you can use Symbolic Splice to solve a lot of different types of analog problems. And this is Supplemental Problem 12.6.